Welcome to this presentation. In this model, we'll be looking into loop antennas. Here, to consider this loop antenna, now the field patterns of a small loop is derived very simply by considering that the loop is square and it consists of four short linear dipoles. And the same field equations were then developed by somewhat longer method based on the assumption that the small loop is equivalent to a short magnetic dipole. Finally, the general case of the loop antennas with uniform current is treated for loops of any size. Okay, and the far fields of circular and square loops of the same area are the same when they are small but different when they are large in terms of wavelength. Now let us consider a small loop. Very simple method of finding the far field patterns of a small loop stated in this presentation. And consider a circular loop of radius A with a uniform in-phase current as given in this small figure, and the radius A is very small compared to the wavelength lambda. Suppose now that the circular loop is represented by a square loop of side length D, also with a uniform in-phase current as shown in this second figure, that is you can see here. And in this way, the loop can be treated as four short linear dipoles whose properties that we know already, and the area of the square loop is same as that of area of circular loop, such that d squared is equal to pi a square. If the loop is oriented like here in this figure, the far electric field has only E phi component. To find the far field pattern in the OIZ plan, it is necessary to consider only two of the four small linear dipoles. That is, you can see here that 2 and 4. We can consider only 2 and 4. Okay. A cross section of this loop in YZ plane is represented here. Since the individual small dipoles 2 and 4 are non-directional in the YZ plane, the field pattern of the loop in this plane is the same as that of two isotropic point sources. Therefore, E naught is equal to E phi minus E phi naught into e power j phi by 2 plus E phi naught into e power minus j phi by 2, where E phi naught is the electric field from individual dipole, and j psi by 2, the psi is given by 2 pi d by lambda into sin theta. This is given as dr, where dr is nothing but 2 pi d by lambda, right? And it follows that E phi is equal to minus 2j E phi naught into sine of dr by 2 into sin theta. The factor in this equation indicates that the total field E phi is in phase quadrature with the field E phi naught of the individual dipole. And this may be readily seen by a factor construction of the type. And now if d is far smaller than lambda by 4, it can be written as E phi is equal to minus j E phi naught into sin theta, because for smaller values of theta, sin theta can be represented by theta. Okay. And the far field of an individual dipole is given by E phi naught is equal to j into 60 pi I L divided by R lambda. And in developing the dipole formula, the dipole was in z direction, whereas in the present case it is in the x direction. So the angle theta in the dipole formula is measured from the dipole axis and is 90 degree in this present case. So the angle theta is a different angle with respect to the dipole being this in this figure, and thus we have the far field by this far field is given by this equation. Okay, where I is the retarded current on the dipole and R is the distance from the dipole, and substituting this equation in E phi, and we'll get E phi is equal to 60 pi into dl sin theta L into dr sin theta divided by R lambda. where the length of the L of length L of the short dipole is the same as D. That is, if L is equal to D, and dr is equal to 2 pi by 2 pi d by lambda, and the area of the loop is d squared, then it becomes E phi is equal to 120 pi squared into I divided by r sin theta into a by lambda squared. And this is the instantaneous values of the E phi component of the far field of a small loop of area A. The peak value of the field is obtained by replacing I divided by I by I naught, where I naught is the peak current in time on the loop. The other component of the far field of the loop is H phi, which is obtained by dividing this equation by 120 pi. So H phi is equal to E phi by 120 pi, which is given by pi I into sin theta by r into a by lambda square. And this chart shows the different far field of small and short dipoles. And let the loop of radius A be located with its center at its origin of the coordinates. That is, let us have a close look of this figure. And the size of the loop is not restricted to a small value compared to the wavelength of this section and this presentation. And let us consider this case. The current I is uniform and in phase around the loop. And since the current is confined to the loop, the only component of the vector potential having the value of value is A phi, right? And the other components are 0, that is A theta and A r are 0. For loops with perimeters of about lambda by 4 or larger, phase shifters of same type must be introduced at intervals around the periphery in order to approximate a uniform in-phase current on the loop. Assuming that the current is uniform and in phase, the far field expressions will be derived with an aid of the vector potentials of the electric current. The vector potentials will first be developed for a pair of short dipole dimensionally opposite electric dipoles of length d phi, and then integrating over the loop, the total vector potential is obtained, and from this the far field components are derived. Since the and the value at the point P and P of the phi component of A from two diametrically opposite dipole is given by dA is equal to mu dm divided by 4 pi r. Okay, where dm is the current moment due to one pair of diametrically opposite infinitesimal dipole of length A into d phi. In the phi is equal to 0 plane, the phi component of the retarded current moment due to one dipole is A di phi I into A di phi cos phi. And on this dm is the current moment due to one pair. Okay, and this figure, this is the cross section of the loop in the xz plane, and referring to this equation, the resulting moment dm at a large distance due to a pair of diametrically opposite dipoles is dm is equal to 2ji into a d phi cos phi sin psi by 2, where psi is equal to 2 beta a cos phi sin theta radians. Okay, and introducing this value of psi, will get dm is equal to 2i into j into a cos phi into sin of beta a into cos phi into sin theta d phi. And by substituting this value, I will get the component A phi is equal to j into mu ia by 2 pi r into integral 0 to pi sin of ba into cos phi, ba into cos phi into sin theta into cos phi d phi. And a phi is equal to j mu ia divided by 2r, and by integrating we will get j1 into beta a cos sin theta, where j1 is the Bessel function of the first order, and of argument F naught into BA into sin theta. This integration is performed on equivalent dipoles which are all situated at the origin but have different orientations with respect to phi. The retarded current I is referred to the origin and hence it is constant in the integration. The for electric field has only phi component and it is given by E phi is equal to minus j omega into A naught, and substituting this value of A phi, E phi is equal to that is phi into psi into Ia divided by 2r into j1 beta A into sin theta. That is E phi is equal to 60 pi beta A into I divided by r into j1 into beta A sin theta. This expression gives the instantaneous electric field at a large distance r from the loop and of any loop of any radius A, and the peak value of E phi is obtained by putting this equation I is equal to I naught, where I naught is the peak value on time of the current in the loop. The magnetic field H phi at a large distance is related to E phi of the intrinsic impedance of the medium in this case, and therefore H phi is equal to beta A into I divided by r j1 into beta A sin theta. And now the far field patterns of the circular loop analysis with the uniform current, and this far field pattern of for a loop of any size given by this equations, and for a loop of given size this beta A is constant and the shape of the far field pattern is given by the equation j1 into c lambda into sin theta, where c lambda is the circumference of the loop in wavelength, that is c lambda is equal to 2 pi A by lambda, that is equal to beta into A. The value of sin theta as a function of theta ranges in magnitude between 0 and unity. That is when theta is equal to 90, the relative fields is j1, and as theta decreases to 0, the values of the relative field vary in accordance with the j1 curve from j1 of c lambda to 0. This is shown in this figure that you can see, and let us find the pattern for a loop of 1 lambda in diameter, and this diagram shows you the different radiation patterns for different sizes, and it is possible to obtain the pattern of a graphical construction. This is illustrated in this figure. We have just considered of c lambda minus pi by the auxiliary circle quadrant of this figure, and the angle theta is laid off around the arc of the circle. The radius of the circle is equal to c lambda and sin theta sin of 90 minus c lambda, which is in the case of that is pi. The field in this direction theta minus 60, for instance, is then given by drawing a perpendicular line to the axis of the and continuing this perpendicular until it intersects the j1 curve and giving the values of the relative field. In this case for 0.443, and turning into the consideration of loops of other sizes, it is to be noted that this is maximum field, and for theta is equal to 90 for all loops which are less than 1.84 lambda in circumference. As an example, the pattern of the lambda for lambda is equal to 10 in diameter is presented here, and the pattern is practically a sine pattern which should be obtained with a very small loop. By way of contrast, the pattern for a loop of 5 lambda in diameter is shown in the fourth figure. In this case of which is typical for large circular loops with uniform current, and the maximum fields in a direction nearly normal to the plane of the loop, which while in the direction of the plane of the loop is small. All patterns are adjusted to the same maximum, the space patterns for the cases, and a figure of revolution of the patterns around the polar axis. It is to be noted that the field exactly normal to the loop is always 0 regardless of the size of the loop. Thank you.